Hello, this is Mr. McGovern, and this is the fourth video in the Momentum and Impulse series where we're going to look at the forces that occur during collisions. So we've got a few collisions to look at. Let's start by looking at the equipment we are using. So in this I'm going to show you some videos in a second, some screenshots of two carts that I'm going to crash together, and I'm going to try and give them the same speed. They definitely have the same mass, and on the front of each cart is a little force meter. And that will measure pretty accurately what forces the cart experiences during the collision. We've got to define a positive direction, so we know what positive is and we know what negative is, so I've chosen positive to be to the right. So here's a quick little video of me setting up the equipment, and you can see I've pointed to the right. I push on one of the force meters and you see the blue down the bottom, it goes positive. I push the other way on the other force meter and it's measuring -3. So again, push on one, +3. And I push on the other, and it's going to be negative something. Okay, so those are going to push together. I'm going to push those carts towards each other, and those two little bumpers will hit, and they'll measure the forces. As they're pushing against each other, and we've chosen positive to be to the right, one's going to measure positive, and one's going to measure negative. Okay, so in the first collision, the carts are just the same mass, the same carts. I'm going to try and give them the same speed. And so as a quick check to see what you think, which do you think feels the largest force during the collision? Is it the cart on the left, the cart on the right, or do they feel the same force?
Okay, so this is equal mass, equal speed. Here we go.
So it's very clear from that these forces are equal but opposite. So it looks like they have a peak force of about 12 newtons. The blue one has a positive force of gets to about 12, and the red one to about -12. But the graphs are completely symmetrical. They look very much identical to each other, except one's negative and one's positive. So why is that? This is Newton's third law, which everyone sort of has heard before they even come to a classroom, that every action is an equal and opposite reaction. But I like to be more precise with my Newton's third law, and it's that for every force on object A by B, there's an equal and opposite force on object B by A. So that's really taking our initial definition of a force, which was a force is an interaction between two objects. So it's really remembering that there's two objects within any interaction where forces are involved. Okay, so collision 2. This time we have the carts, they have the same mass, but only one cart is going to be moving. The other cart I'm going to hold in place with my hand, so you can see it on the diagram there. So which feels the larger force now? Is it the one that's moving when they collide? Is it the one that's standing still when they collide? Or do they both still feel the same force?
Okay, so now this is the recording from the last one. I'm going to hold one steady. This one's going to be held steady. And so only one is going to move in this collision.
Okay, so the forces weren't as large in that collision because only one cart was moving, but the forces between both carts are still about the same. Okay, so again we see a very symmetrical pattern in our force graph. Alright, and the third one is we're going to try and push them together with about the same speed, but one cart's going to be much heavier than the other. Let's have a look at that.
Okay, and this one I've got masses here, so I'm going to make this one here quite heavy. These are quite heavy masses. I think they're 125 grams each. That doubles the mass of this whole cart. So this cart is now double the mass of the other cart. Okay, so we'll set this up. And so different masses, equal speeds.
So again, even though one's much heavier than the other, they still have the same forces, equal but opposite. So Newton's third law still applies even when they're different masses. So why is it so confusing? I mean, we know that everyone would agree that for every force on object A by B, there's an equal and opposite force on object B by A, but it just seems so counterintuitive. Surely the heavier one applies a bigger force. What happens is we actually don't see forces with our eyes. What we see is accelerations, and accelerations are changes in velocity. So with this collision here, you saw the heavy one come in and hit the light one. The light one flew off really quickly. That's what you saw. Now you think that was forces, but that was actually acceleration. So we know that total force is mass times acceleration. It's better written that the acceleration we see is due to the force divided by the mass. Now the heavy one has some force, which we know is the same as the light one, but a very big mass. When you divide by a very big number, you get a very small acceleration. So it doesn't change its velocity very much. The light one has exactly the same force, but we don't see that. What we see is the acceleration, and that's due to it being divided by a very small mass. When you divide by a very small number, you get a very big number. So what we're actually seeing here is the accelerations, and we saw the light one fly away much faster. They definitely, though, have the same force due to Newton's third law.